Hi there. For my presentation on how to confront student misconceptions, my initial thought was at the beginning of every year in chemistry, the first major topic that I address is the idea of physical versus chemical changes and focusing on the mass changes that these may or may not have associated with them. And there's one particular lab that I like to do that takes us about a week. It's kind of been modified, but it's been adapted from the modeling curriculum instruction. And I'll talk a little bit more about that in my presentation. But the purpose of this lab is for the students to perform a series of changes, and I group them together in day one and day three, and I alternate discussions after each of those days. And the students have some prior knowledge, but they aren't really told specifically that day one are all physical changes and that day three are all chemical changes. But throughout our discussion, I start to kind of weave those terms in there for them to make these larger connections. So in day one, they do things like pull apart steel wool, melt ice, dissolve sugar into water, and then evaporate the water out of a small sample of salt water. And then on day two, we talk about the results that they saw, talk about the masses that they recorded before and after to see if there were any noticeable differences and if there should have been a difference. And then we draw something called a particle picture, which they have not had any experience with in the past, but it's our way of developing a working model for them to explain the process that they performed in the lab. And then on day three, they have a slightly different set of changes. They burn matches, they burn steel wool, they dissolve Alka Seltzer into water, and then they form a chemical precipitate. And then again on day four, we discuss and draw particle pictures. The reason that I share this general layout for my lab is that this entire week is just filled with potentially new information for some of my students, but it also is filled with a lot of things that indicate to me prior misconceptions that the students will oftentimes have year after year. And that really has nothing to do with the middle schools because our middle schools do a great job of teaching them physical and chemical changes, but a lot of times they just have a hard time keeping that content with them. And then when they get to my class, there's just certain things that they have a lot of prior knowledge from that they oftentimes misconstrue when we get ready to discuss the results that they saw. And so I have three major misconceptions that I usually confront with this lab each year. And so I wanted to start off with my first misconception, and that is when you burn something, the mass will decrease. So students are oftentimes immediately they go to ideas like, well, when I burn a log in a log or in a bonfire, the log has a certain weight to it, and then after it's burnt, smoke goes up in the air, and then there's just a bunch of charred, ashy log left over, and it's like usually really lightweight and brittle, and it falls apart. So they go with that misconception and then apply that concept to everything that burns. And so the awareness of this whole thing is just a consideration of other factors, and that not always one correct answer or one particular instance is going to be the applying a rule for every time something burns. And so this is something that is pretty common early in their education. Sometimes elementary school teachers, middle school teachers will oftentimes introduce the differences between physical changes and chemical changes and signs that a chemical change has occurred in middle school. But I know firsthand that this process or this misconception, sorry, definitely persists through to high school because when I do a little bit of a pre-lab before we even get into the day in which we burn things, uh, 99 to 100% of students always say like, well, whenever you burn it, something will decrease. And so day three of my mass and change lab is where I start to really break that process down and change up their misconception that just because something is burnt means that it's going to lose mass. And so the lab procedure for day three is really the first strategy for me to restructure this misconception. Again, the lab is called the Mass and Change Lab. So the students evaluate different systems, masses before and after. And so I have two stations in day three, which is my chemical change day, where they burn two different objects and they see that one has the mass decrease and the other one has the mass actually increase. And I'll have them do these reactions or do these changes on top of a digital balance, which is also just like this wonderful visual kind of striking. I don't know how to describe it. It's just like when they see the numbers change on the scale as something is burning, it just really just sets it into motion that this is a change that they're witnessing, and it kind of destroys that misconception right out of the gate. So first thing that they're going to do is burn a set of 10 matches. And so they gather 10 matches, we'll have them put them in an evaporating dish. They place it on the scale, and then using one of those matches, they strike it on the side of the matchbox. They reach down in there and they do their best to try and ignite all of the matches as they're burning. And usually, once all 10 go up in smoke, they start to see that as the smoke goes up in the air, the numbers on the digital scale start to go down. And so a lot of times as I walk around, students will have this kind of like, "Oh, yeah, see, okay, so it's burning and the mass is going down and smoke's going into the air." And then when we get ready to rationalize that later, they have a better idea of explaining why that is. But then when they move on to the next station right after that, they take a sample of steel wool. Again, I have them place it inside a little ceramic evaporating dish. And then using a pair of crucible tongs, they'll pick it up, wave it over the edge of their Bunsen burner just to catch the corner of it because we make the steel wool kind of a little bit more open and porous, so it has a wider surface area. And then once one corner of that ball of steel wool starts to ignite, it does a really good job of tracking. It almost looks like little tiny fiery kind of snakes or worms are kind of weaving their way through the steel wool. And I'll tell them to put it back on the scale that they started the mass with, and they see that as it starts to kind of light and ignite and burn in front of their eyes, the mass on the scale, the numbers actually start to climb, and the look on their faces is usually pretty shocking because they're assuming that because this piece of steel is burning, that there should be smoke that's being released and that the mass should be going down. And then, really, when we come back the next day and we start to discuss uh, the observations for these reactions, that's where it starts to kind of really reconstruct their misconception of this uh, idea that if something burns, the mass should go down. So the observations and the mass data before and after is really my second strategy. Not only do they see the reaction, do they see the differences, do they see the number on the scales change, but this process of drawing out a particle picture um, helps them not only be able to explain without using words, but really illustrate using their own kind of prior knowledge the process that's taking place. And so we've already at this time had a day of drawing particle pictures, so they have an idea of how best to illustrate solids and liquids and gases. But when they get ready to draw the matches burning, they have a pretty good idea of drawing, a couple of particles that are bound together to represent something that's in the solid state. And then in the after picture, they know that smoke is released. So they draw a bunch of gas particles and smoke particles and things like that up above. And they have a pretty good job. They do a pretty good job of explaining the fact that if the matches weighed a finite mass beforehand, then the mass difference of what it weighed after would be the mass of the smoke that went up into the air. But the reason that I have them start with the matches is to rationalize the fact that if the mass went down because the gas went up into the air, some groups then connect the idea that the mass of the steel wool went up, not because something else was added onto the scale, but because the gases in the air that allowed the steel wool to burn in the first place must have added onto the steel wool particles. And so they get the idea that it's kind of a flipped process, but because the starting material had some carbon in it, and carbon dioxide as a gas likes to go up and leave the system, and the steel wool is made out of iron, which is a different material, that just because it burned, it might have had a difference in its mass change. And so both of these days together does really help to kind of break up that misconception, but really cement the idea that just because you perform the same action on the different set of materials doesn't mean that you're going to get the same results in the end. All right, my second misconception is probably one that's way more widespread throughout all high school chemistry classes, and that is that sugar dissolving into water is a chemical change. A lot of times students come at me with the disappearance of something. Like, says sugar dissolves into water, you can't see it anymore. That because you can't see it anymore, that must mean that there's a chemical change that's going on. The sugar's gone. And so this is part of the original Mass and Change lab before I kind of modified it from the modeling curriculum, where they take a sugar cube, they mass a beaker of water all together on this scale, and then they drop the sugar cube into the water. And then before and after, they see that the mass really stays the same. But the misconception is that, well, if the sugar cube is visually disappearing into solution, then it must lose mass. And so students come up with this idea that the mass should go down and that there's a chemical change in this process. And so one of the articles that I found that researched this actually had students kind of interview results for this particular type of a physical change. And a lot of middle school students, when presented with this lab, also agreed that this is, in fact, a chemical change because something disappeared, that it's gone, that you can't reverse it. So this is definitely something that starts to kind of showcase itself at the middle school level. And then again, from my experience working with my students, I know that this misconception also persists through to the high school level. And I really start to break down this misconception at day two of our lab. Because again, they get the results from day one, they drop a sugar cube into water. But when we start to discuss that result in day two, that's where we start to kind of reframe their understanding. So the first strategy, again, is always that I use the lab, the data, the numbers, and the observations to really drive their explanation of their discussion of things. So I say using their mass analysis, they measure a mass of a sugar cube in a sample of water. And before and after, one sugar cube dissolved into 100 milliliters of water weighs the same or mass is the same before and after. And then the next station that they do in this lab, they have a little dropper bottle filled with saturated salt water. And we talk about, well, is there any way for us to separate the salt from that water if it's dissolved? And then make that connection to the idea that, well, could we separate the sugar that you just dissolved into that sample of water? So the students will put about 20 drops of saturated salt water into a test tube, get the mass of that system, and then using a Bunsen burner, they'll evaporate and drive off the water, and it leaves behind, it's kind of a nice visual experiment. It leaves behind a bunch of white salt crystals at the bottom of their test tube. And then they put it back on the scale and they see that the mass has drastically gone down because the water is completely up and evaporated out of the tube. So again, the numbers and them actually seeing the visual and performing the change with their own eyes helps to kind of restructure their understanding of this misconception. But then the driving force behind this whole thing is that discussion using their particle pictures, their illustrations of what did they see and what numbers did they collect. So they use their observations and their mass data, and then observationally, they saw that the salt wasn't visible before, but it crystallized after. So when they are asked to draw the sugar cube dissolving into the water as a particle picture, again, this is still early in the week, so they're still kind of figuring out how best to even draw these particle pictures. But they get the idea that if the mass stayed the same, then the sugar particles and the water particles together should equate to the same total mass afterwards. And so we're also kind of building up their understanding of the law of conservation of matter without even mentioning that as like a definition. So then when they get this idea connected over to the salt water in their test tube, they have a pretty good idea because this will be the fourth particle picture that they draw, that if the mass went down, then they need to somehow remove the particles in their after picture. But then I usually come back and make the connection like, does the water just disappear from existence altogether? And then there's usually every year a couple of students that are like, no, I noticed that there was steam coming out of the mouth of the test tube. And so then we say, like, okay, so the matter didn't fully disappear. It wasn't eliminated. It just was changed. And as a gas, it left the test tube. So then I have them go back to the drawing board and draw the same number of particles still before and after. But if they're drawn now as a gas, which will be the first time that they illustrate a gas as a particle picture, then there's no way that its mass could go onto the scale because the particles are up and flying around the air. So it just kind of helps to frame their understanding of not only as these changes are occurring, how do the states of matter as they change also affect the system before and after. All right, and then for my last misconception, as we go throughout the lab, this misconception really starts to kind of uh, dance around in their heads quite a bit. Because at this point, about halfway through the week, I've already gotten some students to bring up the idea that there are things like physical and chemical changes. They'll start to kind of research it on their own a little bit. And then a lot of students then start to make the assumption that matter is lost in all chemical changes, that must be the connection, that physical changes, mass is the same, and in chemical changes, matter is lost. And so the awareness of this is describing a change that they're going to do in the lab with more than just calling it a physical or a chemical change. There's more ways to describe a reaction. And by this point, if we're on like day 3 or towards the end of the week, I'll start introducing this idea of like an open system versus a closed system. Because the lab, again, is structured enough so that some of the physical changes lose mass and some of the chemical changes lose mass. And so the big kind of culminating discussion of this whole week is them being able to differentiate an open physical system, a closed physical system, an open chemical system, and a closed chemical system. Right. So the same article that I researched actually mentioned something about this. So I kind of went with the idea that this misconception starts somewhere at the middle school level and again persists through to high school because I have students that start out my year making the same assumption. And I usually get them on board with this whole idea of how we can interpret the mass, if it should or should not change, not just from physical versus chemical, but open versus closed by the last day of the lab. And so the main idea for this is to come up with, or the main restructuring idea is to come up with some chemical change that takes place inside a completely closed system. And this particular station where they form a precipitate, and this is on day 3, it's in my chemical change day. This really sells home the idea of open versus closed. So again, we're going to use mass analysis. We're going to compare masses before and after. But I prep ahead of time 2 different solutions that are completely colorless. One is sodium carbonate, the other one's calcium chloride. And then I have the students pour about a third full of one solution into one vial with a lid, and a third of the other solution into the second vial with the lid, and then put both vials with lids completely closed off onto the scale to record their initial mass. Now, the sodium carbonate and calcium chloride solution, when combined together, will form a solid precipitate of calcium carbonate. And I don't mention any of this at all. We kind of avoid all of the chemical names and the lingo as much as possible because it's, again, about the second week of our school year. But we bring up the idea that if they open both the vials and then pour one liquid into the other, the image down here to the right shows this kind of white, cloudy solid that forms. And my students then make the assumption of did they make milk or what's going on and what's happening inside the vial. But then they put the lids back on the vial, put it back on the scale, and the mass stays perfectly the same. And so this is the first time that they see an actual chemical sign, a chemical change, and the mass of everything combined together is still the same. To them, a lot of the chemical changes are things burning or things rusting or things fizzing, and all these things involve external factors. And this is a solution reaction that's completely internalized and kept inside the liquid that they started with. So as long as they don't do something like leave the lids off of the vials or spill one of the solutions, their masses most of the time are usually pretty much the same, maybe a hundredth of a gram more or less, but we usually can factor that out in terms of errors on behalf of the scale. So that's the main strategy, is presenting them with a chemical change that keeps constant mass, and then going back to this particle picture where they have to illustrate the fact that they had 2 colorless solutions that just looked like liquids, But then as the vial that had both chemicals combined together settles out, there's this solid sludgy stuff at the bottom. So it's not only a great way to present them the idea that things can be dissolved into water and can look like nothing's in them whatsoever, but then if those chemicals are reactive with one another, then sometimes that chemical product can be a little bit more visual. So observationally, there was definitely a chemical change. They say that it looks like milk, but according to their mass data, for this one, they made something completely different from two solutions, but the mass stayed the exact same. So the masses of the dissolved components combined together, but stayed the exact same. So those are the three misconceptions for the entire lab. And then by the end of the week, we go back to this whole process and really start to break down the fact that day one we're all physical and day three we're all chemical, but not all of the masses for day one stayed the exact same, and not all the masses for day three stayed the exact same. So there's really a lot of complexity broken down into this week, which is why I like to give myself a day after each set of stations to go back and discuss, draw particle pictures to rationalize the changes that we observed, and then come up with a group's agreed upon working model to how to draw these things best for future representation. But throughout the entire week, as they're doing all these stations, there's a lot of other really good skills that are reinforced through the process. So when they're burning for the determination that not all things burned result in a mass loss, proper data collection really is done outside of just this first misconception. A lot of times I have students that will, add something on to the scale and then leave it off and then switch it around. And if they don't record their numbers, the first time they wrote it down, they think, well, it said that I think it was 14 point something something. So encouraging them that it's important that as data is collected to write it down for their record and their memory, but also the proper use of a balance. Prior to my class, the number of kids that just plop something onto the scale and read whatever number is written is kind of alarming. I always use the example, although I'm sure someday it's probably not going to work out super well, of like you don't hop on a scale at home if it's already reading 20 pounds, because then it's like, well, I weigh 20 pounds more than what the scale tells me I actually weigh. So I always encourage them that they want to zero or tare, make sure that the scale reads perfectly zeros across the board, and to use a weigh boat that's also tore so that whatever we add to the scale is the weight of just that added material. As we go throughout misconception number two, the dissolving sugar to determine if it's chemical or physical change, one of the most important things is proper experimental technique. So it's something as simple as what you put on the scale at the beginning in terms of equipment should go back on the scale afterwards. So when we dissolve the sugar cube into water, we use a watch glass resting over the top of the beaker, and then we put the sugar cube on top of the watch glass so we get the mass of the entire system, and then they tip up the watch glass to drop the sugar cube into water. But I always ask my students, like, what's going to happen to the mass if I forget to put the watch glass on the scale for the second reading? And most of the time, the kids jump on the fact, like, oh, the weight's going to go down. It's like, but is that something that we want to have added in as a variable if we're trying to see if this particular change results in a change in the mass? So that usually alone is enough for kids to realize, like, oh, if this was on the scale for the first measurement, it should probably go on the scale for the second measurement. Um, when they get ready to drive off the water inside the test tube, teaching them proper technique in terms of heating a solution inside a test tube. Most of the time, the students haven't done a lot of actual chemistry labs at the middle school level, so this is their first real exposure to it. And so, not only does our safety video talk a lot about pointing the test tube away from you and away from others, but then I get a lot of students that want to go with the like straight up and down method, and I tell them that the best technique is to still keep it at an angle, because if for some reason whatever's in the test tube does decide to explode, you don't want it to go up and then rain down on top of you. I was like, unless everybody brings an umbrella to class, this is probably not the best technique to be utilizing. So they still have to get used to that and using the test tube tongs effectively so that they don't drop anything. Um, a lot of times I still have to kind of pause and tell myself, like, this is their first time getting into a lab, so I'm not expecting them to be professionals. They are going to make mistakes, but little things like that I try to utilize throughout this week to teach them so that they hopefully remember that as a process going forward. And then the last one throughout misconception number three, proper experimental technique, just evaluating things as you change only one variable, especially analyzing a wide range of data. So when we get ready to not just compare one station and how the mass changed for that station, but comparing the fact that the stations where a gas was absorbed or released was more talking about an open system as opposed to physical versus chemical. And so they're presented with a lot of concepts throughout the week, but being able to go back and evaluate whether or not physical means a mass change, chemical means a mass change, or if it's more open versus closed system will dictate if it's a mass change. So they usually we this schedule said for 4 days. It's usually about 5 or 6, because as we discussed, after the first station's worth of days, or the first day's worth of stations, usually we have to go back to that just to kind of redraw and reinforce the patterns that they saw. So I didn't have a whole lot of references. I did want to reference the American Modeling Teachers Association, of which I'm a member, because I utilize their modeling curriculum a lot throughout the year. It does a good job of having kids develop models to be able to explain and rationalize the patterns that they saw. So I got their lab from them and kind of worked and tweaked with it myself. And then I got this wonderful article called Changes Matter, addressing student misconceptions about physical and chemical changes, from an article from Science and Children magazine. I hope you enjoyed my presentation. Thank you so much.